Hello, welcome to another episode of the Data Science Leaders Podcast. I'm your host, Dave Cole, and today's guest is Alon Malki. Alon is the Senior Director of Data Science at National Instruments. How are you doing today, Alon?
Great, I'm doing fine. Thanks for inviting me here.
Great. So Alon is based in Israel, and what we're going to be talking a little bit about today is first of all, we're going to start. We're going to discuss data science in the manufacturing of electronics, which is Alon's world here, and what he's been doing for probably at least the last, I'd say, 10 years or about. Does that sound about right?
Quite close, yes.
Yeah, quite close. All right. So I'm pretty close. And then we're going to talk. There's something interesting that Alon has some experience with in sort of sharing data, right, between parties in order to sort of improve the overall manufacturing process. That is one of the things that he is working on, and I think, and we're going to talk a little bit about why that's important. And I think there are some universal sort of data science related issues with regards to ground truth that Alon has a lot of experience with, at least in the world of electronics. That I think is sort of interesting. And then we're going to talk a little bit about building models in the lab versus production. If we have some time, we'll talk about human in the loop, data science. So why don't we start at the top? So why don't you just ground us all, Alon, in just kind of what your world is? What are talk a little bit about just the basics of the manufacturing of electronics, and then where data science plays a role.
Cool. So the area we are working in is industrial IoT. It's where you manufacture semiconductors and electronics. Optimal Plus, which is the company that I acquired, was in that field for only 15 years. The customers that we serve are customers like NVIDIA, Qualcomm, practically all the leaders in semiconductors and in electronics, Bosch, Continental, and companies like that. So we have agents at the factories connected to the manufacturing machines and testing machines, or to databases and systems that collect data. We take the data directly from the sources. We have a layer of edge analytics on the factory floor that includes rules and models and predictions, etc. But we stream the data also to the cloud or to the data center of the customer, where there we have the big data analytics. Because we stream data from many factories, and we have long retention periods in the cloud. This is where we actually bring the tool for big data analytics, for machine learning, building the models. This is where you will build the model, where you have all the data and the compute power. And then in a click of a button, you can push the model or the rule into the factory floor, so it can run in near real time as part of the manufacturing line.
So these agents that you have at the manufacturing side, what exactly are they?
So it depends. In testers machines in semiconductors, for example, we actually have an agent deployed on any type of tester. It's running on the tester itself, hooked to the machine, to the operation system, and to the software of the tester. And it actually collects everything what happens during the testing. In other areas, we can connect to the logs of the certain machine or to APIs of a certain machine. The main idea is collecting all the measurements or test data that is relevant for the process.
Got it. So you're basically getting in sort of these agents are sending sort of in real time. They're streaming the results of the tests, and they're also streaming some logs for some of the other machines. So you mentioned edge analytics. So talk to us a little bit about like what you mean by edge analytics. I mean, I have a pretty good idea, but like maybe not everyone is familiar with that term.
Sure. So let me explain for a second what are the use cases that we do, and it will help us go through that. So the thing that we are trying to do is saying, for example, identifying units that all the tests and everything says that the unit is okay, but we can do some prediction and predict that this unit is going to fail in production. So we try to catch escapes, units that are bad but looks good to the process itself. We have capabilities to improve, optimize the process itself, we have capabilities for doing adaptive manufacturing, which is like monitoring certain parameters that are typically drifting in production, and from time to time calculating and adjusting the knobs, like changing configurations of the machines in real time. These are things that when they are done manually, it takes days to identify that there's a drift and calculate the things that needs to be fixed. And when we put a model, it happens in seconds or minutes. It saves tons of money and increases the quality, because when it's not tuned, you may have failures in the field. So some of these prediction or analytics or the insights can happen later on. It can happen like a day later or a week later, and these ones can run in the cloud. But there are things, or most of the things needs to run inline as part of the manufacturing, because a unit does not need to move to the next station if our model says that it's a bad unit, or if you want to skip a unit. It needs to be inline. So this is the edge analytics. One important thing I want to mention is that most of the companies that are doing analytics in the industrial IoT field are actually monitoring the machines themselves. So in a factory, you have tens or maybe hundreds of machines. They produce parameters and logs, and most of the companies collect this data and try to come up with use cases like predictive maintenance and things like that. We, on the other hand, we track the products themselves. So those tens or hundreds of machines, they produce millions of units every day, and we are tracking those units. So if you think about semiconductors, for example, just in the testing stage, you have millions of units, each one of them passing like 10 stations. In each station, you have thousands of tests. All these huge amounts of data, this is the data that we collect. And we track not only the chip, we can track it also when this chip is placed on a board, and the board is placed in a system, and the system is built on a product. We track all this genealogy. So this is, we call it the product lifecycle, and we track all the phases, and it allows you to make decisions according to that.
Got it. So the focus is not, so I think what I heard you say is that most companies will just focus on the predictive maintenance of the machines themselves. But what you're calling sort of lifecycle analytics is looking at the products that are being produced. So the specific semiconductor or the specific piece of electronics that is being produced in the manufacturing floor, and all the tests that it goes through, and then there's an opportunity for you and your team to then identify whether or not that specific product that has been manufactured is sort of good or bad, and worth going to the next step in the process. Do I have that right?
Exactly. And again, we are not here to replace the testing themselves, that they try to decide if the chip is good or not. We come on top of that. Mm-hmm. We come in places where the test program says this unit is good, and we say, hey, we look at it. I know you think it's good. It's not good. Don't send it to be in an airplane, for example.
So then what happens then, right? So what happens if the testing machines themselves say it's passed all the tests, but then, when you're looking at your models are sort of analyzing the data essentially, and they predict that, you know what, this is not as good as it looks bad. Then what?
So usually before we actually deploy the model, we prove the customer that the models make sense, right? That the results make sense because using historical data. And then we deploy it. So in many cases, once our rule with the machine learning model decides that this unit is bad, it will be scrapped. They will kill the unit. Okay. In other places, they can just do a retest or examine it by a human, etc. It depends on the cost of the unit.
Right. So these are the tests, though, that are happening on the manufacturing floor for the products, right? But then the product goes out into the real world, right? And you can test these products, hundreds of times in a bunch of different ways, right? But until they go into the real world, there still may be sort of products that sort of electronics that sort of slip through the cracks that still end up having errors or issues. So how have you addressed that problem?
So first of all, we don't address all the problems. Some things go to production and fail, right? In many cases, when we have our customers have failures, they get reports on that, and then we do root cause analysis, and we try to analyze those RMAs versus the batches that were produced together with them. and we try to identify the root cause or and the main idea is to identify which are the other units that maybe we can do an early recall to avoid the unit to fail in production, maybe even not send it out of the factory, because eventually some of the units, they have a failing unit that still didn't get out of the factory. And if you identify bad units in the field, and you identify that the problem is a certain batch of a component, you can track the other units. It's much cheaper to catch them before they go out to the field. And of course, when you're doing those root cause analysis, we also allow the customers to improve their process. So next time, this type of error or mistake will not happen again. Now, one more thing.
So, go ahead.
Just one more thing. Before you go to actually the field, remember that the customer of a chip manufacturer is usually an electronic manufacturer. So production for the chip manufacturer is sometimes just the next factory. And in this case, it's easier to catch it because the electronics manufacturer can have a problem with the board, and then realize that the problem is actually in the chip that came into the board. And here comes data sharing, etc. That maybe we'll get to it also.
Yeah. So that's what I was going to segue into, which is the data sharing element. So you have the manufacturer of the chip. The chip then gets sent to the next to their customer, right? Which may take the chip and put it on a number of chips, put it on a board, and then they run their tests, and then they identify that one of these chips is bad. If you're the manufacturer of the chip, you want to know that chip was bad, right? So then there is some sharing of data, correct?
Exactly. So it's even more than that. Sometimes the electronic manufacturer doesn't know that the chip is a problem. He tests his board. He puts the chip on the board. He assumes the chip is fine, and then he gets failures on the board. He tests the board, and there are problems. So in some cases, we suspect that the problem is not in the boards themselves, but maybe on the chips. Then we need to convince the chip supplier to share his data, like share different test parameters or manufacturing parameters of those batches of the chips that he sent to that customer. Once we have that, we can do the correlation between those chips results and identify that, hey, this series of problems in the boards can actually be correlated to a certain geographical location of the wafer of the chips.
And there's a geographical location, like on the wafer, like not the chip itself. So it's sort of a bad sector or something like that on the wafer.
Yeah, a wafer in semiconductor, a wafer is a piece of silicon where you print the chips on top of it before you cut them out. So the wafer itself, there's a geographic issues about it. If there's a problem in a certain area of the wafer, it's a material. So sometimes we identify boards are failing, and we see that all the chips that are placed on the failing boards are located in certain areas on the wafers. So we know that there was a problem in the wafer itself, on the semiconductors manufacturer, not in the electronics manufacturer.
Got it. So, in the end of the day, like for your team, right? So there's data coming from the agents and the original factories themselves, right? There's models that your team is building that are actually sort of improving the tests on the factory floor of where the chips are being made. They also are actually changing certain configurations that you mentioned to sort of improve the overall quality of the chips being made. And then you're also getting you're getting the results of the data. Right? You're getting the results of the data that then the customer who is receiving these chips from the original manufacturer, and you're sort of combining that all. So that I have to imagine there's you're doing this to try to get to ground truth. You're trying to get trying to understand which of these chips were successful, which sort of failed, which had issues, and why do they have issues, right? In order to improve your model. So there's got to be a lot. I mean, there's a lot going on there, right? There's multiple different parties where you're receiving the data from. What are some of the challenges that you've faced in this entire process? Like what, for those data science leaders out there that are trying to sort of improve their models and dealing with I have to imagine, massive amounts of data coming from all over the place. So what are some things that you sort of have learned over the years?
So I think the most important things we learned, and we learned from in the hard way, is that you cannot just take a bunch of data to your lab and try to build a model. Because reality in the manufacturing world is very, very dynamic. Things are changing all the time. People may assume that, once you set up a manufacturing line, things are static. The reality is completely different. Machine maintenance state is changing, configurations are changing, operators are changing, even test programs are changing from time to time. So everything is changing. Mm-hmm. And if you, for example, if you take 3 months of data and try to predict the next month, sometimes it will work just fine. Sometimes you will realize that the data is changing so fast that if you take 3 months, you cannot actually teach a model. So you will actually decide to build a model from 3 weeks of data and predict the next week, and then throw it again and use the next model. But this is just one example. Other things that can happen is that you may, for example, you can build a model and you have a very good accuracy for a per unit, and then you realize that practically in the manufacturing floor, in this specific operation, you cannot make decisions on a specific unit. You need to make decisions on a batch. So all the model that you build is completely different now. So what we learned is from day one, not even, there was a stage where we would build the initial model, just, looking at the data, splitting the data, train data, test data, etc. And then only then trying to adjust it to production after we have initial results. We even dropped that method because sometimes you just completely start from the beginning. So today we are getting the data. First, we are learning what exactly happens in the use case, what exactly happens in the factory floor, what are the rate of the data changes, what are the constraints, and only then we start to develop the model from the first minute exactly as it will behave in production. So this is one important thing.
Yeah, so there's something interesting here, right? So I think for most of us in the data science world, like we all not assume, but we hope that they're like, the data engineers that we're working with, like the data quality is the format of the data is relatively static. I mean, yes, there are use cases where the data can change. You're dealing with semi-structured data and the like, but that's not quite what I'm talking about here. You're dealing with sort of structured data, and because of what's going on in the manufacturing floor, the data itself is sort of evolving and changing. There might be new tests or a new machine that was added, and I have to imagine that you have to get ahead of that in some way. You have to build in safeguards to say that, like, hey, the data has fundamentally changed. We need to retrain our model. So how have you built those safeguards? How have you found a way to proactively recognize it? I mean, I can't imagine you're waiting for a human to give you, sends you an email or something and say like, hey, we just added a new machine. FYI, you're getting a whole different data set, and let me explain it to you. So what have you done to sort of adjust to the changing
this is a great question. So we built quite a strong infrastructure for us to manage the life cycle of the model on the factory floor. So once we deploy a model, together with the model, we deploy another pipeline, which is a scheduled monitoring pipeline, continuously checking a bunch of things, starting from data distribution changes, scores distribution changes, and also control groups. It depends on the use case. So we continuously monitor different things and try to identify cases where we need to retrain the model. By the way, we also do a scheduled retrain anyway and see if the new model behaves better than the old model. But if we see that there's a drift or something is changing, we automatically retrain the model on the new data, try to come up with a new model, check the performance, and if it's better, we trigger the user to replace the model. Otherwise, we alert him to call the data scientist as fast as possible.
Got it. Yeah, that makes a lot of sense. I mean, I think that most data science teams have started with scheduled retraining, but I think the more sophisticated teams out there are actually monitoring drift in sort of real time, and then triggering the retraining of their models accordingly. So that's very interesting. I want to talk briefly too, just what words of wisdom do you have? I mean, one of the things that I know you mentioned that you want to be careful about is, that I want to underscore is the changing of the sort of the training data set and just being careful that like we just mentioned that those models based on the training data set, I mean, because things are so dynamic, they're not necessarily going to work in production. But what other sort of words of wisdom do you have for data science leaders that you sort of collected over the years?
Yeah, so one important thing that we also realized is how hard it is to actually make users adopt models in production, especially when those models are coming to replace decisions that were made by humans before that. It takes quite a long time because users find it hard to trust those kind of models. They don't have the time and priority to give you feedback and allow you to conclude results when the model behaves differently than the original human decisions. So originally we would run our models in shadow mode, just in parallel to the human decisions in the factory floor. Then we realized that once you have discrepancies and you come to the users, they don't have time for you. Sometimes they find it hard to admit that they did a mistake. And sometimes they even argue between themselves what is the right decision. Because one of them gave you the labels, one of them is making the labels when you train the model, one of them is making the decision today. So who is the right one? So eventually what we are actually doing, almost with every model that we deploy, we bring it together with a human-in-the-loop application. And the main idea is that instead of starting with a decision-making application, we're starting with a decision support application. So the model sits on the production line, gets the inputs, makes the decision. Instead of sending it to the manufacturing management system, it sends it to a human being. The human being has a nice interface where he can either approve our decisions or correct the decisions. Only then we take the final decision and send them to the manufacturing line, to the manufacturing systems. What we get with that is that, first of all, we can bring the model. It doesn't have to be perfect when we start with it. It can be, quite good, but it doesn't have to be perfect. Then we let the user give us his corrections. We improve the model with the corrections from the user. We don't need to waste his time for solving discrepancies because he's just working in his line, actually has a better interface and even a system that helps him. So it's easier for him, but still he gives us all the feedback that we need. And the more we improve the model, we also improve the confidence score that we bring to be more accurate. So eventually we start bringing a threshold, so less and less decisions are actually going to the user. And eventually only very low confidence score decisions are going to the user. Most of them are just going automatically.
Right. So in order to gain the trust, right, of the human on the manufacturing floor that previously was making decisions all on his own, instead, you start just by reporting, hey, I think there's a potential issue, with this chip or with this batch or what have you. And then you have the human say, yep, you're right, or no, that doesn't look right to me. And that is helping to train your model, right? So you're helping to get sort of, direct human feedback, but also it's helping to gain the trust, right? So that, that individual is seeing that and over time noticing that the model is getting better and better and better. And then you actually are then, depending on the confidence score, you're deciding whether or not to directly, flag. I'm throwing this out here, Alon, but just flag whether or not that chip is bad or not. And if it's if it's sort of a low confidence, then that's when the human actually goes in and says, yeah, you're right, or no, you're not right. And then eventually, does it ever get to a point where the human is not in the loop, or are you always sending those low confidence scores to the human?
So in many cases, we get to a point that mostly, practically all the data, all the units are just passing automatically. In many cases, this is the case. Right. There are use cases that are too sophisticated, and then there are cases we don't want to take the risk. Again, in our industry, a mistake can be very expensive. So we always prefer to take the risk. But in many cases, if you reduce the manual effort by 95 or 98%, this is a huge saving. And it's also an improvement of quality, because people make mistakes. Models, once they are tuned correctly, they make much less mistakes than humans. We have tons of examples of that.
Well, this has been fascinating. One of the things that I'm just been thinking about, right, is that like your world, Alon, is sort of a data scientist dream. I mean, most data scientists love to know that like the work that they're doing is having a direct sort of impact. And it seems to me like, your world is one where you can measure that impact in a pretty concrete way. I mean, yes, there are going to be gaps, and there may be downstream customers from the manufacturing floor who may not share that data and may not get ground truth. But by and large, you're actually seeing those results sort of in real time. But not only that, it's not a static thing. There's it's a very dynamic environment where you're constantly having to to improve upon the models that you're building. So, when it comes to recruiting and you're looking for data scientists out there, is there anything that you particularly look for? I mean, do you look for people who have sort of background in electronics or manufacturing, or is that just merely a nice to have?
So background in electronics is nice to have for me. The most important thing that I'm looking for is people that are motivated by challenges. The most important thing that we have is someone that, there's a problem, there's a challenge, he jumps on it. He will read whatever he needs to read, he will try whatever he needs to try, he will fight until he wins. This is what we need, because we are working with customers in production. We have different use cases every day coming. We have new things that surprise us all the time. So this is what I'm looking for, practically.
That's awesome. Well, Alon, I've thoroughly enjoyed our conversation. I've learned a lot, and the world that you live in, certainly sounds exciting and dynamic to me. And I would love to be, if I was a little younger, I'd love to be a member of your team. So thanks so much for being on the Data Science Leaders podcast. I really appreciate it.
Thanks for hosting me here. It was great. I really enjoyed it. Thanks.